Alrighty, today we get to find limits using the property of limits, including the DSP, which is the direct substitution property. So we're going to go ahead and take a look at all of these properties of limits that we're going to be introduced to today. Whoa, so cool. Okay, let's break these down. Remember, we're practicing looking at something and not being overwhelmed and actually breaking it down. So, the way we calculate limits without using a calculator is called limit laws or properties of limits. They're one and the same. So here's what you do. If you're adding two functions inside of a limit, you can split that up. So it's almost like distributing the limit. I hesitate to use that word, but we're tying it to something we already know. The same thing happens with subtraction. You get to split it up, that limit. So sum property, different property, constant multiple property. We use this one a lot, so I'm going to give it a little asterisk. And what this one says is if you have a constant times your function, like 2x, it's okay to put the 2 on the outside and then find the limit of your function. This will all make more sense momentarily. Multiplying, you can multiply, you can divide as long as your bottom limit does not equal 0. So that's the quotient property. Then we have the power property, which says this: if you have something raised to a power, then it's okay to take your limit of whatever it is and then raise it to a power. So that would be like if I had x squared, I would take just the limit of x first and then square it. That's what the power property says. I'm going to star 7, and I'm going to star 8, and I'm going to star 9, and I'm kind of going to double star these two because we really use 8 and 9. Everything boils down to 8 and 9, but number 7 I'm starring because we use it very often. Anytime there's a radical, you have to rewrite your radical using this property. So it's saying if you have some sort of root in a limit, you need to take the limit of just your function first and then do the root. You can't do it any other way. Okay? This is saying for integers. Z represents integers. I think I kind of already told you that. And we also assume that the limit of this is greater than 0. Remember, the whole square root has to be greater than or equal to 0 business. That kind of thing. That's where that comes from. I'm not asking you to memorize any of these. I'm just asking you to apply some of them. So the other property that we're really going to love is the direct substitution property. But before we truly can appreciate that direct substitution property, let's do just one without using the DSP. Okay, so this is how we do this. So again, we're just exposing you to these right now. Before some really smart mathematician came up with direct substitution property, this is how the other people had to do their limit rules. So let me show you. First of all, the limit of x squared plus 2x plus 4 over x plus 2. And this is the limit as x is approaching 2. So first of all, do you notice we have a numerator and a denominator? So what we would have to do is, using that quotient one, our first step would be to whoa. What am I doing? I'm just blindly copying. Sorry, peeps. It's all right. It's okay to make mistakes, right? I'm going to say that in a lot of videos, but it really is. It's really good for your brain. Hopefully I don't make that same mistake twice. This is what I meant to do. We're using that quotient property. So it says justify each step. So I'm going to do this little hash. Looks like parallel lines right there. Hashtag, just kidding. This is the quotient property. You're like, okay, I'm picking up what you're putting down. The quotient property up there says if you have one limit, you can split it into 2. You got to put the limit on both the numerator and denominator. Okay, cool. And then things are about to get crazy. We have the limit as x approaches 2 of x squared plus the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 4 all over the limit as x approaches 2 of x plus the limit as x approaches 2 of 4. Whew! And that, my friends, was how we apply the sum property. Now, that was kind of tedious. And again, we won't be doing this always, but look, this is what the sum property says. If you're adding individual functions, then you can split them up within each limit. Now, we're going to backtrack just a second before we continue because I just realized I made a mistake and I forgot to finish going over 8 and 9 because I was so excited about telling you about number 7. So number 8, this property right here says the limit of a constant is the constant. So I'm going to draw you a quick little picture here for that. Let's say I'm saying the limit as x approaches 2 of, I don't know, 5. So my function is y equals 5. Remember, that represents your function. It's f of x. So when y equals 5, we get a horizontal line. So it looks like that. So as x is approaching 2 from the left, my intended height is 5. And as it approaches from the right, my intended height is 5. What if I change that and I say, I don't want it to be from 2. I want it to be from -1. Guess what? With a horizontal line, what is the intended height always? 5. Horizontal lines, when you see them like this, these are the constants. So it makes complete sense that no matter what value of x you're approaching, the limit of a constant is the constant. Sweet. Okay, next one. The limit as x approaches a of x. Remember, that's our function, so that's y equals x. That's this line, diagonal line, right? What if I say the limit as x approaches 1 of x? What does this rule say? It says it's whatever number is down there. So it should be 1. Let's see if what we learned from yesterday confirms that. So as x is getting closer and closer to 1, my y value is also getting closer and closer to 1. What if I change this to 2? This should change to 2. Okay? So we have the limit of a constant is a constant, and the limit of x is equal to whatever value you're approaching. Great, let's get back with our problem. So here we just finished up with the sum property. Now do you notice we have a power here? So we need to look up at number 6 and look at that power property. And what that says is that you should first take your limit as x approaches 2 of x, and then after you're done, you can see why I wanted it to just be x, number 9, and then property number 9. And then this right here, I am going to use the constant multiple property. So that's number 3. We put a little star by it. I'm going to pull out the 2, which is a constant. Take the limit as x approaches 2 of x. This is a constant, so I'm not going to mess with it because the limit of a constant is the constant. And down here, I already have just x. So now, what did I use? I used the power and constant multiples properties. Constant multiple. Once I've gotten it down to 8 and 9, I get to use 8 and 9 because that tells me up here, if you have a constant, the limit simplifies to just the constant. It is only when I'm getting to this step where I'm actually performing the operation of limit that I, get to take and not write my limit sign anymore. So this is what it looks like. I'm going to draw myself my fraction bar. The limit as x approaches 2 of x. That's number 9. It says the limit of as x approaches 2 of x equals, well, we're just going to use inference here and see that that's 2. So 2, and then I have the square on the outside, plus 2, the limit as x approaches 2 of x again, there's property number 9 again, is 2. The limit of a constant, remember, that's like this horizontal line, at 4. What's the limit? It's going to be the constant 4. And this one is 2 again. And then this one is 4. And this was me using properties 8 and 9. And then I just get to simplify that. So that equals 12. Ooh, I wrote 4. Where did I change this? Oh my goodness, did you guys see that? Way back at the beginning, you're probably going, Wolken, why are you writing 2? I mean, why are you writing 4? It's okay. So good for us. I did that on purpose. I wanted to see who was paying attention. I hope you caught it. There we go. Easy fix. And that equals 3. So that limit is 3. I could have plugged this into a graphing calculator and looked from the left and the right by making a table and seen that. Now, we can all agree that that was super annoying. I may have thought it was a little bit fun, but I know I'm in the minority with that. So enter the direct substitution property. Dun, da, da, da. What does that say before we get to use it? Because just like that IVT where these conditions had to be met, this thing's got some conditions too. So it says, if f is a polynomial or a rational function. What the heck is a polynomial? I've heard that term so many times, but what is it? Polynomial. Stuff like this. That's a polynomial. That's a polynomial. That's a polynomial. So what a polynomial is, it's called the sum of monomials, which are like, great, thanks for introducing monomial. Monomials are terms, and the way that that is defined is the product of a number and a variable. And so when I write something like this, here's a counterexample, non-polys, something like this is a non-polynomial because really it's like this. So it's not the product, it's the quotient. So you can't do that. So you won't have like radicals. Radicals are not polynomials. They have to have whole number coefficients. So we learned whole numbers was 0 and the counting numbers. So keep that in mind, okay? So we need to look at the rest of this. Okay, so polynomial, rational function, ratio. So this is defined as a ratio of polynomials. Sweet. Okay, take a look at this one right here. If I just look at the numerator, that's a polynomial. It has a whole number exponents. You're multiplying. There's no radicals or anything like that. And the bottom is also a polynomial. So because that's a ratio of two polynomials, this is a rational function right here. So that's the first part. It has to be a polynomial or a rational function. So I'm going to write that. So condition 1 is polynomial or rational function. You're like, okay, cool. So like looking at my paper, rational function and not a polynomial and not a rational function, that square root down there. This one, polynomial, polynomial, therefore the thing together is a rational equation, a rational function. So next, what's the next piece of it? And A is in the domain of F. So A, which is representing the number it's getting close to, A is in the domain of F. So that means, I'm going to write this over here. These are your two conditions. So that means that f of a exists. So let me show you with this. What value of x is not in the domain of this function? It would be -2. So is 2 in the domain? Yes, the only number that's not in the domain is -2. Over here, We're not even going to mess with this one because it's not a polynomial or rational function, so I can't use DSP, so we'll go into that in a second. We will manipulate it so that we can then use DSP to make our life easier. But look down here. 2, plug in 2. What's 2 minus 2? 0. Not in the domain then. F of 2 does not exist, so it's not in the domain. So again, we're going to use math to manipulate this to hopefully be able to use the DSP. So we did all this work over here. Let's do a 1-2 check. So if we're going to do the DSP, I like to do my 1-2 check. 1, 2. Okay. So the first thing is does it meet condition 1? Polynomial or rational function, check. Doesn't meet condition 2. Is A, which is the x value you're approaching, in the domain? Yep, it is. So if I wanted to use DSP, what does this say? The DSP says if you want to below the limit as x approaches A, just plug in A. That's what that says. How silly, right? We do all this work, and then we just could have done all this work by going this. The DSP way, we could have just done this. 2 squared plus 2 times 2 plus 4. So I'm just plugging in 2 right here. This is what it told me to do. All over 2 plus 2, which equals 3. Cray, cray, right? So that was so much easier, but we do sometimes not get to use the DSP, so we need to appreciate and understand how to go about it the long way before we can go to the short way. Because even with radicals, students will say, hey, Wolken, when I just plug in -2, I get the same answer as all this work that you're about to do. Why can't I just plug in -2? And the answer that I have for that is that no mathematician yet has proven that the direct substitution property works for all radicals. They may have gotten it to work for most of them, but they haven't come up with a proof to show that it will work for any, so they can't write it as a property in math. That would just be bad taste. So right now, we don't get to use it when we have radicals, okay? So let's see what we can do. So like I told you guys before, we are going to do the 1-2 check on these. So the first thing, I like to do it like this. 1, 2. This does not meet condition number 1. And I'm writing some words here to help you realize why it doesn't. We are not taking the limit. You don't have to write this, but it's super helpful when you're looking back at your notes. We are not taking the limit of a polynomial or rational function. So we can't use DSP. Yet. And I'm going to put a ... there. So what do? We have these limit laws that we fall back on. And the limit law that we're interested in is number 7. And that says if you have the limit outside the radical, it's okay to take the limit and put it inside the radical. So this may seem like a minor detail to you, but this actually is awesome because now when I do my 1-2 check, order of operations tells me to take the limit first and then square root. So if I'm taking the limit, am I taking the limit of a polynomial or a rational function? Yes. So that limit just applies to that. It no longer applies to the radical. So now I'm doing that. And is -2 in the domain. So can I plug it in? Yep, that's in the domain. So I'm just going to put this right here. Now we are taking limit. And this is specifically a polynomial because it's not a fraction. It's not a numerator and a denominator. So now we can use the DSP. Isn't that cool? So instead of having to split it up by all those radicals and split that limit along each one and using the constant multiple property for that, we can just go like this. Leave your square root because that goes there. And we can evaluate our limit. Ta-da! Okay, this is going to be a longer lesson. I can already tell. I have so much to say about this. Anywho, okay, we're going to move on. This problem right here. We need to do our 1-2 check for DSP. 1, 2. Wow. I'm actually, yeah, we're good. 1, 2. This is a polynomial. This is a polynomial because we're dividing. That means it's a ratio of polynomials. What about number 2? Is 2 in the domain? Therefore, f of 2, that's what we're asking here, equals undefined right now because it gives us division by 0. So we cannot do that right there. Makes 0 in denom. Boo. So we can't use the DSP yet. But we're going to be cool. And we are going to manipulate. So we don't have to worry about, some students go, hey, can we split this up using the quotient property? And I like your thinking. That's a good thought. It's a mistake, but it's a good thought. Because even if you split it up, you're still going to end up with division by 0. So what we're going to try and do is manipulate our rational function. So we could rewrite this. I'm going to give myself some space here as the limit as x approaches 2 of x plus 2 times x minus 2. So I'm using that good old difference of squares. Hey, look, those cancel. And I have the limit as x approaches 2 of x plus 2. What? So if I do my 1, 2 check, 1, and then does f of 2 exist? Yep, it's 4, so that's a check. So we can say now we can use the DSP. Okay, so we're just going to do 2 plus 2. Remember, once you use the DSP, which is direct substitution, I directly substitute in, you don't write the limit anymore. And I made a mistake and wrote an extra parenthesis there. So we get 4. Okay? Bada bing, bada boom. Flip it over. Let's get this lesson going. What is this? This is crazy. It's okay. We got all of this. It's no big deal. We're like super good mathematicians. So, first of all, the 1-2 punch. Bam, bam. That is a ratio of 2 polynomials. Does f of -4 exist? Nope. Bam. So what are we going to do? We are going to try and manipulate this. So this is the limit as x approaches -4, and they're rigged. Can you see that that's rigged? Plus or minus cubes, factors, little and big, parentheses, ab, a squared, ab, b squared. The signs go soap. What happens? These cancel. Now you always, I know you're going to want to try and jump to direct substitution before you get this step, but you're doing due diligence here, right? We're diligent in our procedure because we have realized that it makes us make less errors. So the time we would have saved might give us a mistake. Even the time we sometimes don't save, we get a mistake, but we're less likely to get a mistake. And we don't want mistakes on tests because those cost us. So now it's a polynomial. So here it was a rational function, but now it's a polynomial. And then f of -4 does exist. Okay, I'm going to put a check mark because I don't want to plug in -4, which I'm going to do anyways, but, you know, I'll do it in this step. -4 squared minus 4 times -4 plus 16, which equals 16, plus 16, plus 16, which equals 48. So then normally I would have you guys do a group challenge on this next one, but it's kind of hard to do that when you're not at home. So here is what we have. 1, 2, punch. Okay, so 1, 2. We have as x approaches 2. So rational function, check, is 2 in the domain. 2 squared is 4 plus 4, which is 8. So f of 2 exists. So yes, that's awesome. I don't know why I wrote an equal on that one. It's just a does it exist or does it not? And it does. So guess what? We don't have to manipulate this at all. We get to go straight to DSP. So here I am, here I am. Sorry, I was going to start rapping. I probably shouldn't. I'll save that for my fam bam. I'm sure they would love for me to share it with you so they don't have to hear it, but it's all right. It's one of the perks, right? That's 0. Your limit can be 0. There is a y value of 0 on a graph, so your intended height can be 0 for a function. So I know sometimes it's hard for us. It's like yesterday we were graphing and today seems completely different, but it's really not that different. You're still finding the intended height. The one you're just looking at a graph and one you're using the equation. But I could put this in my graphing calculator and verify it using the table method that I did yesterday. Oh my gosh, I get to number 6. Or letter E, which is not number 6. I don't know why I thought that said number 6, but you know, it's the 3rd video I've recorded today, so we'll give Miss Wolken a little bit of grace on this, right? Okay, this one says the limit as x approaches 0 of this. So guess what, guys? 1, 2. First of all, this doesn't meet condition number 1 because it's not a ratio. This is not a polynomial, so it's not a ratio of polynomials. You see that square root? You should send up a red flag, and trickies are the ones that we're testing you on most of the time. But BTW, f of 0 also doesn't exist. Look at that, f of 0. If I plug in 0, I get that. So way back in, get this, P6, I'm going to write it here for you. Go to P6 and look at the very last problem. How do I manipulate this? Well, what I do is I multiply by the conjugate. It's called rationalizing the numerator. Do you remember it? I told you guys we'd be using it again, and we practiced that skill. What skill we got from that is this. When I'm about to do this, I am not going to multiply that x to that term right there. I'm going to leave the denominators as factors. So let's see what happens. So in the numerator, because I've created conjugates, I've created difference of squares, I'm going to get 16 plus x, good with that, minus 16. And in the denominator, what I just told you, the skill that we picked up way back in P6 was to leave it in factored form. Why would you leave it in factored form? This is because 16 minus 16 is x all over x times square root 16 plus x plus 4. The x's will cancel and I'll have a 1 left in the numerator. So once I've completed that simplification process, a lot of times students think, okay, now I can use the DSP. The problem with this is that although you may be meeting condition 2, you still haven't met condition 1 because this is still not a ratio of polynomials. This is a radical expression. So guess what? We have to do like we did in that very first example, and we have to break it up. And because we have a denominator, we have to break this up too. And now watch, just like we did in example 2, following the limit laws, I am putting 16 plus x under the radical. Make sure to extend your radical if you don't. Probably a little smoother than me, but and what you're noticing is that I have to make sure every single term gets that limit. So once I'm here, finally, I got the 1, 2. Okay? So what do we do from here? I'm just going to bring this up here. The limit as x approaches 0 of 1 is what? That would be 1. The limit of a constant is the constant. And then I'm going to have to do the square root and then plug in 16 plus 0. And then the limit of a constant is the constant. So 1 over the square root of 16 plus 4, which equals 1 over 4 plus 4, which equals 1/8. Woo! That's impressive, right? Okay, we're plugging and chugging right along. Letter F is very similar, so I'm just going to work through it, see if you could pause the video. It's actually easier maybe not than E, but it's pretty similar. So first of all, my 1-2 punch, it doesn't meet either requirement. Boo. So I see a radical in the numerator. Go ahead and try and multiply by a conjugate. It's kind of an easy conjugate compared to the last one. No, I always have to have my limits here. Proper math notation. This would give me, what would it give me? T minus 9. Oh, remember we keep these as factors, so I have T minus 9 all over square root T plus 3. Do you guys feel like these are rigged? Because you should. They are. Look at that. If you didn't factor, you get a 1. If I do the 1, 2 now, condition 2 is met, meaning f of 9 exists. Right there. Sorry, I should probably say t. It's fine. But what doesn't is it's still not a rational expression or a ratio of polynomials. So I'm going to split that bad boy up. This step you have to do to get full credit. I think you get only half credit if you don't. So remember, limits go under radicals when we do this step. There's not so much that I can really say. I mean, I could always find time to talk. The limit of a constant is a constant. This one, I'm plugging in 9 for t. Limit of a constant is the constant, so that gives me 1 over 3 plus 3, which is 1/6. Okay? Okay, pumpkin. Moving on. This one looks super intimidated. People are like, something about this screams difference quotient. I don't know if I like it, but it's okay. So first of all, first question, is this a ratio of polynomials or is it a polynomial itself? So this is a ratio of polynomials and it's kind of in disguise. So watch this. If I do this and I FOIL it, I'm going to get 9 plus 6h plus h squared minus 9. So I'm not going to be a puppy killer right there. I'm going to FOIL that out all over h. So when you look at it now, when you see this in term form instead of factored form, that looks like a polynomial. I know it doesn't have x's. It's just because we changed that to an h. And that's because we're progressing to a change to h. But anywho, that's that right there. So it does meet condition number 1, but does f of 0 exist? No, it would be undefined. So that doesn't work. So what do we have to do? We have to figure out how to manipulate it. So a good idea, so the first way is if you can multiply by a conjugate, but we've only really seen that tool when we have had a radical. So what I would do is actually simplify. And if you look, 9 and negative 9. Oh, this is beautiful. So we have 6h plus h squared over h. These have a GCF. Yeah? Okay. So this is the limit as h approaches 0 of 6 plus h. And now I'm going to do my 1, 2, and it meets both conditions because f of 0 exists now, and that means I can use the DSP. So this is 6. Sweet. Also a tricky here. This really shouldn't be a tricky. We have been doing complex fractions for a while now. You should know how to do those. Don't get fooled by these. Remember, anytime it doesn't have a denominator, give it one, and so on and so forth. So first of all, if I do the 1, 2, condition 1 is met. Because this is a ratio of two polynomials. I should say that. And let me rephrase that. It is not met yet because this is 1 over x to the negative 1. Like this would be x to the negative 1 and you can't have integers. But also what I want to point out is that condition number 2 isn't met because x minus 3 is in the denominator. And if at any point along the way it makes the denominator 0, then it has to be excluded from the domain. So both of those conditions are not met. But we know that we can manipulate this to write this as a single fraction. So again, you have to keep that limit even when you are doing simplifying stages. So that would give me 3 minus x over 3x times 1 over x minus 3. Now, watch this, because students see this and they're like, those are similar. I kind of want to just cross them out. First of all, this 3 is positive, this 3 is negative, so they're not exactly the same thing. Here the x is negative, here the x is positive. But here's a skill that you should pick up fairly quickly in this class, is that if I factor out a negative 1, I'll write the negative 1 there. I'll write the 1, but normally we don't. Then if I pull out that would be negative 3, and that would be x. And another way to write that piece right there would be, I'm changing it just back to negative, I can't stand it. If I rewrote it the order, it would be x minus 3. So do you guys see that? So these are really just opposite quantities of each other. You need the negative. You could even change that one if you wanted to. It's just not common because your x term usually comes first. So let's apply that. So this is negative x minus 3 all over 3x times 1 over x minus 3. Cancel, cancel. Sweet, common factors, but don't forget that negative. It's the limit as x approaches 3 of negative 1 over 3x. Just remember in math, I know that was in the numerator, but you can put it right next to the fraction bar. And now I'm doing my 1, 2. And in my 1, 2, it meets both now. So I get to use direct substitution. And I get negative 1/9. That would be the limit. Hey, if it's on the graphing calculator portion, make sure to trace to get closer and closer to the value, because at 3 it's not going to exist because you can't divide by 0. But if you did something like 2.999 and 3.001, then it would work. Okay, greatest integer function. We already did greatest integer function, but we're going to be doing limits with greatest integer function, and I didn't actually draw a graph for you guys. So I'm going to draw that graph really quickly. Basically, the greatest integer is the largest integer less than or equal to x. So we round down. That's what we said. So if I had something like 1, 1.1, 1.2, 1.5, 1.9, 1.99999, and then like 2. Let's say those are my numbers. Why am I picking them? Because it's the greatest integer function, so I want you to see how it works. 1 is an integer, so it stays at 1 because it says less than or equal to x. 1.1 would get plugged in and get rounded down to 1. So would 1.2. So would 1.5. So would 1.9. So would 1.99999. It doesn't jump up to 2 until you're at 2. So what does this look like on a graph? So I'm just going to plot this part of it. At 1, it's 1. So there's a closed dot. And then at 1.1, it's 1. So we get 1s all the way until we get to 1.999. And then it's going to jump up to 2. So that's what it's going to look like. And it's going to repeat that step pattern infinitely. And it's going to go back the other way like that, etc. So find the following. 3 is an integer, so that's a 3. 3.7, it gets rounded down to 3. 2.9 gets rounded down to 2. Negative 0.1. So that's kind of hard for people, but remember you need to go to the left to be less than. So here's 0, here's 1, here's negative 0.1 right there. You need to go to the left. So this is, by the way, that should be negative 1, negative 1. And then negative 4.59 is negative 5. So now with that, we're going to use limits and use this graph real quick to be done. The limit as x approaches negative 1 from the left. So I'm going to continue my graph real quickly just to get this in here. Okay, here's negative 1, boop, 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 left, right. As it approaches negative 1 from the left, look at that. It's going to a height of negative 1. So from the left, negative 1. Oh, but you know what? This one says from the right. I'm so used to it saying from the left and then from the right. Did you hear? Like, I was totally thinking about it. So let's change this to a left and this to a right. That'll make more sense for us. So as it comes in from the left, it's negative 2. As it comes in from the right, it's positive. It's negative 1. So at negative 1, the limit does not exist. Okay? So we did change those. You could also just change your answers if you wanted to do that as well. And that is all we have. Have a great night.